So now we're going to talk about the TNB frame, which is going to tell us a little bit about how our particle is moving along our curve in space. So this frame consists of three vectors that are going to be derived from our parameterization, which we always denote R of t. The vectors are denoted big T, big N, and big B. Each of them can be evaluated at the point. So I'll get a different vector at each point in space. And we already know one of them. So we've already seen capital T, which is the unit tangent vector. The other two vectors that we're going to be studying are called the binormal vector. There's numerous definitions for the binormal and the unit normal, but these are the definitions that you want to use to compute by. So you'll see that when your book does the treatment of this, it'll present the definition slightly different, but I'm giving you the definitions I want you to use for computation. So the unit binormal vector is going to be the cross product of r prime with r double prime. And then, of course, that won't be a unit vector necessarily. I want to make that a unit vector, so I'm just going to divide through by the length. Okay, so you can think of this as the velocity cross the acceleration divided by the length of that resulting vector. The unit normal vector we can compute once we have the unit tangent and the unit binormal. And the unit normal is just the unit binormal cross the unit tangent. So equivalently, we can define the unit normal using this formula here, which is actually the formula your book is going to first give you, which is it is the derivative of the unit tangent divided by the length of the derivative of the unit tangent. Now, this doesn't look like a very complicated formula, but the problem is that you really have to leave the unit tangent as a function of t. Otherwise, when you take derivatives, you'll just get 0. And so when you take that derivative, I mean, you have to remember the unit tangent you've divided through by a length. So you're going to have, quotient rule in each component. And now you're going to divide that thing by the length of something that has quotient rule in each of the components. So you can imagine that for many functions, this expression quickly becomes extremely unwieldy. So it's much better to compute with the formulas that I gave you on the previous slide. But using this definition, it'll be easier for us to see the relationship between n, t, and b. So the one thing that we know about the unit tangent is that it has length 1, right? So let's remind ourselves that the length of the unit tangent is 1. And for simplicity, I'm going to drop the fact that all of these things are evaluated at t, because we're not going to really need that in this computation. And so what this means is that t dot t is equal to 1, right? Because t dot t is the length of t squared. And so we can take derivatives, and taking derivatives, we get, dt of t dot t equals d dt of 1. So on this side, we get 0. But when I apply the derivative to this dot product, what I get is that I get t dot t prime plus t prime dot t. Okay, and since the dot product commutes, then what this tells us is that I have 2 t dot t prime is equal to 0. And so that can only happen if t dot t prime is equal to 0. This tells us that the unit tangent is orthogonal to the derivative of the unit tangent. Then what this tells us is that t is orthogonal to n. I guess all of these are vectors, so they should have all had vector symbols on them. Okay, so this is really important that we can see that this is orthogonal to this. And from the definition, we know that n is going to be orthogonal to b and t from the cross product. And so ultimately what we're going to get is that all three of these are orthogonal to each other. So they're really going to create something that looks like the x, y, z axes at each point along our curve. So using the TNB frame, we can create some planes that are going to tell us a little bit about the motion of something traveling along our curve using the parameterization R of t. So the first one is the normal plane. And this is the plane which is going to be perpendicular to our curve. So if you imagine our curve is coming like this, the normal plane is always going to be orthogonal to it. Okay, so like if it was a train track, you'd be putting sort of like a flat board on the train, and then it would just be following the train track around. And we can imagine that we have really, twisty, curvy, crazy train tracks. And this plane has the vector t of a, so the unit tangent as a function evaluated at our point A, t equals a, as the vector which is orthogonal to this plane. Okay. The osculating plane is going to be the plane which best captures sort of the motion of the curve. So this one is a little bit trickier, and I'll show you some Mathematica demos in a separate video, which will show you what the osculating plane looks like in certain examples. But it's going to sort of, as our curve curves up, if I wanted to sort of imagine that the curve lived inside a plane, then at each point, that plane would be the oscillating plane. And obviously, this is going to change as the curve sort of moves in strange directions. But the important thing to know is that the vector which is orthogonal to the oscillating plane at each point is going to be the unit binormal. And so that will be the normal vector to that plane.